In this video, we're going to start talking about acid strength. And if you remember from 152 or wherever you had general chemistry 2, stronger acids are going to be acids that, if we're using Arrhenius theory, ionize more. If we're using Bronsted-Lowry, more readily dissociate or donate their protons. So if I have hydrochloric acid, HCl, it's considered a strong acid because it's completely ionized, right? All of the hydrogen ions are going to be donated. So stronger acids, these more readily donate their protons. Remember, using our Bronsted-Lowry theory, acids are going to be proton donors, right? They're going to give a proton to that base. The more readily they do that, the stronger the acid. So stronger acids more readily donate their protons. We would say that they ionize more than weaker ones. In general chemistry, you would have measured acidity using an equilibrium constant. So acidity is measured using the equilibrium constant So capital K was always our abbreviation for an equilibrium constant. And if we were talking about the constant for acid dissociation equilibrium reactions, we would put a subscript A, right? KEQ is just a generic one. KSP was our solubility product constant. KB was our equilibrium constant for base dissociation equilibrium equations. So K is just the generic equilibrium constant, and then because we're talking specifically about acidity, we put that subscript A there. So an example, if I was to take HA, A just being a generic conjugate base, and react it with water, my acid HA is going to donate a proton to water. Water is acting like my base, giving me my conjugate acid, hydronium ions, plus my conjugate base, A-. And this is existing in equilibrium. It's going back and forth. So when those rates are equal, we're at equilibrium. And we could write our equilibrium constant for this. Remember, our equilibrium constant, we're always the concentration of products over the concentration of reactants raised to a power equal to their coefficient. These are all 1-to-1. Remember, polyprotic acids donate their protons one at a time. So our coefficients for acid dissociation equilibrium equations will always be 1, right? If I had carbonic acid, H2CO3, it's going to lose one of those protons first to form HCO3-, and then in a second step, we would have HCO3- going to CO3-2-. So we would have a Ka1 and a Ka2 for that, right? It would dissociate in 2 steps. So concentration of products over reactants raised to a power equal to their coefficient, which for acid dissociation reactions is always going to be 1. And then remember, we are excluding water from this. Water is a pure liquid. If I look at the states of matter here, and remember those brackets mean molar concentration. So we're talking about how is our molar concentration changing? Well, water doesn't have a concentration, right? It's 100%, it's just water. So my concentration is not changing at different points in my reaction. So it's not included as part of my expression. And in the forward direction, right, in this direction, this is where it's donating the proton. So acidity, we said, right? Oops, not that one. It's more stronger ones are more readily able to donate their protons, which means the equilibrium would lie closer to the product side, right? Products would be favored at equilibrium for stronger acids, meaning the concentration of my species on the top is going to be greater than the concentration of my species on the bottom. So the larger the value for Ka, the more dissociated products I have, right, the stronger my acid. So larger Kas, right, larger equilibrium constants. And again, if you're looking at values, you might actually see the EQ there for equilibrium instead of an A. Again, just capital K is the equilibrium constant. So larger Kas mean stronger acids, right? What larger Kas actually mean is that products are favored at equilibrium, and the products are what happens when that acid donates its proton. So the more readily it is able to donate that proton, the more products I have. That's making sense. Again, this is all just 152 review. So essentially larger Ka means larger product concentration, right? Which means the acid is more dissociated, more ionized. So we could say, so stronger. Do you guys get why I'm using the word ionized versus dissociate? This is a side note. Dissociate versus ionize. So if we were going to go through the Arrhenius theory, I mentioned it at the beginning of the last video. I said that was the one where an acid ionizes an aqueous solution to produce hydrogen ions, and a base dissociates in aqueous solution to produce hydroxide ions. And I would use different words there. It's easier to explain if we do dissociate first. To dissociate assumes that things were associated, right? So we're taking things that were hanging out together and we were separating them. So if I look at sodium hydroxide, this is ionic, right? I'm not overlapping orbitals and sharing electrons in the overlapping region. I actually have two ions that are hanging out with each other. So when I separate them, all I'm doing is unassociating them, right? They were associated and I'm dissociating them. So when I put it in water, instead of having them with like a bracket around or they're hanging out, they're a little separate. So they were associated and I'm dissociating them. I had ions to begin with, right? This has a charge, this has a charge. And all I'm doing is I'm taking those two charges and I'm separating them. If we were to look at an acid, HCl, these are not charged, right? This is a covalent bond, right? I would have a p orbital, actually an sp. We know that there's, 3 lone pairs in there. So I have an sp3 orbital of chlorine, right? We're gonna do hybrid now. And it's actually overlapping with the s orbital from hydrogen, and those electrons are hanging out in there. I do not have, I'm gonna write this, but it's wrong. This is not what I have, right? That's not an ionic bond. This doesn't exist. So I have things that weren't ions, so I'm making them into ions. So ionized means I'm going from something that was covalent to ions, right? I'm ionizing it. I'm making ions where there wasn't previously ions. No ions here. We're putting it in water and we're getting ions. With dissociate, we're just separating ions that already existed. So I had ions, I put it in water and I separated those ions. It's really common, and I still do it, to use the word dissociate. Like up here, I actually said dissociate, but then changed it. I'm trying to be really good about not using dissociate where it should be ionized, but I still do it. And it's really common. Like we'll say an acid dissociates in water. It doesn't. If it dissociates, that means it was associated, but it's covalent, not ionic. So it's just better to use that word. And it's a tough habit to get into. But it's kind of now the point in your chemistry career to try to start training yourself. And I still goof it up. I'm not expecting you to say it right every time, but I do want you to know the difference. And I want you to understand why I keep correcting myself. So I can dissociate things that were associated. I can't dissociate ions that weren't previously ions, if that makes sense. Okay, side note over. Back to the task at hand. KAs. So essentially, the larger my equilibrium constant, the stronger my acid. The other part that you would have added to that was pKa. And pKa was the negative log of our Ka. So if you were to take your Ka, take the negative log of it, we get the pKa. pKas don't have units. And then the other part to note is that negative sign. So the larger your Ka, the smaller your pKa. Equals stronger acid. So I could give you a couple acids, I could give you some pKa values, I could ask you which one's stronger. So just kind of as an example, and don't worry, we're not going to do ice tables in here, we're not going to have to calculate any of that. We're actually going to do this completely conceptually. So I have this organic molecule and it has a pKa of 25, and then we'll have ammonia, and ammonia has a pKa of 38, which is really big. Ammonia we think of as a base because its pKa is so big, so its Ka is so small, it's actually a really weak acid, right? We think of it more as bases. It's an entire continuum also, right? Just because something we think of as base doesn't mean it can't be an acid. It's just if it's a strong base, it's a weak acid, and vice versa. The two are always opposite of each other. So anyway, out of these two, which is the stronger acid? This one, right? Because it has the smaller pKa. So if I gave you a couple acids and I gave you either pKa's or Ka's, be able to tell me which one is stronger, which one's weaker, it's really just remembering this. That's all there is to it. We're not going to have to calculate it. You don't need to get out your calculator at any point in this chapter. So larger Ka, smaller pKa, stronger acid. The position of our equilibrium depends, let's actually say this differently, sorry. The position of the equilibrium depends on the strength, relative strength of the acid and the base. So equilibrium will always favor the formation of the weaker acid or base. Right, everything we said about acids up here, we could also say about bases. We would just have to replace the A with a B, right? So the larger the Kb, the smaller the pKb, the stronger the base. And then remember that acid and base strengths are always going to be opposite. We would write our expression differently, right? Because we would be gaining protons instead of losing them, but larger Kb's, smaller pKb's, stronger bases. So we're just adding base in here also, because we could do it with bases. So equilibrium will always favor the formation of the weaker acid or base. The way I think about it is that the stronger one gets to do what it wants, right? If the stronger acid, or whichever acid is stronger, that's the one that's going to donate the proton. The stronger base gets to win, right? It's the one that gets to accept the proton. So I just always remember whichever one's stronger wins. So if it's stronger, it gets to do what it wants to do. If it's weaker, it doesn't get to do that. So the stronger acid wins. right? If it's stronger, it gets to win. It gets to do what it wants. If it's weak, it doesn't always get to do what it wants. It's an unfortunate situation we often find in life, but it's true. So the stronger one wins in this case. So an example, using the two acids that I gave us in the last example. So I'm going to take this acid and I'm going to react it with this base. And we end up producing my conjugate base plus my conjugate acid. Right, so this was my acid. If we compare the before and after, that's the one that donated the proton. My base, my conjugate base, and my conjugate acid. And then the Ka values or pKa values that I gave us up above. So for this one, it was 25. And these are about 25, it's not exact. And then for this one is 38. So if I asked you, at equilibrium, what is favored, reactants or products? That's our question. So given the reaction above and pKa values, is reactants, or are reactants or products favored at equilibrium? That is our question. Where does that equilibrium lie towards reactants or products? So you can look at it two different ways, right? We could say that it always favors the formation of the weaker one, or we could say that the stronger one wins. However you want to look at it, we're going to get the same answer. So we had already determined, because this one is the smaller pKa value, that this acid is the stronger one. So since that one's stronger, it gets to donate its proton, and equilibrium is going to be favored in that direction, right? It's going to be the forward direction that's favored. If you want to use our first one right here, right, it favors the formation of the weaker. This one, let's use a different color, is my weaker acid. So again, it's going to favor the formation of that. So it's going to go towards products. So products is our answer, right? Products are going to be favored. And again, your explanation could be either one, right? This is my stronger acid. So it gets to donate more protons. I mean, each one's only donating one, but there's more than one molecule, right? If we had 1 mole, we would have 6.022 times 10 to the 23rd of them. So each one is donating a proton, but more of them are donating protons. Hopefully that makes sense. The other way we could say it is ammonia is the weaker acid, so its formation is favored. I don't really like this explanation that well because it doesn't really tell us why. Like, why is it favored? And it's favored because, well, the other one's stronger and gets to donate more of its protons. This one's weaker, so it doesn't get to. So I don't really like this second one very much, but it's kind of how our book is explaining it. I'm going to actually put that in parentheses because I like the first one better. Hopefully this is making a little bit of sense. Let's do one more. I guess we can use the same color here. So another example, same question. I'm going to give us a reaction. I'm going to give us a couple of pKa values, and we're going to determine which direction is favored at equilibrium. So I guess before that, let's label acids and bases because it's good practice. So this is my acid, its conjugate base, my base, and its conjugate acid. Hopefully you guys are getting those, right? We're just comparing the reactant side to the product side. If I compare this one to this one, as I went to products, it gained a proton. If I compare this one to this one, as I went from reactants to products, it lost a proton. It was donated. And then some pKa values. We are, in the next section, going to learn to do this without pKa values. On tests and quizzes, I'm rarely actually going to give you a pKa value because we're going to learn why. And that's the part I really want us to get. But before that can make any sense, this part needs to make a little bit of sense. So given our two pKa values and this reaction, is reactants or products favored at equilibrium as our question. So what do you guys think? I do want you to think about this one on your own first. Yeah, it's going to be reactants. Hopefully you said that. So again, the smaller the pKa value, the stronger the acid. So this is my smaller value, which makes this my stronger acid. So it gets to donate most of its protons, and we're going to go in this direction. Other way to think about it, this is my weaker acid, so equilibrium is going to form its formation. It's going to go in the reverse direction. So reactants are favored at equilibrium.